Hello boys and girls, so in this video we are going to focus on 2.2 charging and discharging of capacitors. Capacitors can undergo two main processes. We call it as charging and discharging. Charging is a process whereby we store charge in a capacitors. Discharging is a process whereby we remove the charge in the capacitors through a load. So the figure below shows the setup of the circuit for charging and discharging. So the figure on the left hand side shows the passive setup of a circuit for charging a capacitor. It must consist of power supply or a battery, resistor and an uncharged capacitor. For a discharging circuit, basically we do not have any power supply or battery, but we only have resistor and charged capacitor. So boys and girls, sometimes these two charging and discharging circuit can be combined into one with a switch that we can flip in between position A and position B as shown in this figure. As the switch is flipped to position A, we will get a circuit that is composed of a battery, resistor, and also capacitor as I trace out here. Okay, so the presence of the battery will tell us that this circuit here is the circuit for a charging process. However, if the switch is flipped to B, if the switch now is flipped to B, the circuit will now be composed of a capacitor and the resistor and the switch without power supply for this circuit. See, when I trace out, there will be no power supply for this circuit. So, this circuit is a circuit for discharging process. Again, in order for us to determine whether it's a charging or discharging process, we always have to focus on the presence or the absence of the power supply or the battery. So once again, without the battery or any presence of power supply, this circuit is what we call as discharging process. Okay, so I hope you can differentiate between the circuit for charging and discharging. Always focus on the presence or the absence of power supply. Charging process, we have power supply. Discharging process, we do not have any power supply or battery. Now let us see what actually happens when we're charging a capacitor through a resistor. So we have a capacitor connect to a battery of voltage V0 through a resistor R. So as we connect the battery to the capacitors, a current will begin to flow. So what actually happens is the electron will flow through the battery, leaving a positive charge on plate A. However, because of the gap between the two plates, electron won't be able to pass through, so they will start to accumulate on plate B. As the charge accumulates on capacitor, plate B, the potential difference across it will increases and the current is reduced. Once the voltage of the terminal of the capacitors equal to the voltage of the batteries, the capacitor is fully charged and the current will stop flowing through the circuit. This completes the charging process. Now let us see the variations of charge, current and also voltage across the capacitor against time during the charging process. During the charging process, we find out that the charge will increase exponentially with time until it reaches a maximum value of Q0. at time t equal to RC, we will find out that the charge that accumulates on the capacitor is 63% of its maximum value. During the charging process, we find out that the current that flows in the circuit will decrease exponentially with time from a maximum value of I0. At time t equal to RC, we find out that the current is only 0.37 I0 or 37% of its maximum value. Then, during the charging process also, we find out that the voltage across the capacitor will start to increase from 0 exponentially until it reaches a maximum value of V0. Okay, this V0 is the maximum voltage that we supply using a battery or power supply. So at time t equal to RC, the voltage across the capacitor is 0.63 of V0. So we can represent the tree curve with the following equations. So the charge at any time can be calculated by using Q0 in bracket 1 minus exponent to the power of negative t over RC. The current at a particular time can be related with the maximum current using this equation, and the voltage at a particular time can relate with the maximum voltage by using this equation. So class, we might discharge a capacitor through a resistor or a load. So I can connect any electric component as my load. For example, I might connect a light bulb, or I might connect a light emitting diode, LED. For example, I connect a light emitting diode, LED, across the charge capacitor. Observe what actually happened when I discharge this capacitor through the LED. So once it's connected, electron from plate B will begin to flow through the load and neutralize the positive charge at plate A. When part of the positive charge on plate A is neutralized, the process will continue until the charge on plate A is fully neutralized and the voltage across the capacitor becomes 0. So class, now let us see the variation of charge, current and voltage across the capacitor against time during the discharging process. During the discharging process, we find out that the charge on the capacitor will decrease exponentially with time. At time t equal to time constant, the charge is only 0.37 of its initial or maximum value. What about the current against time? The magnitude of current that through the resistor will decrease exponentially with time. At time t equal to RC, we find out that the magnitude of the discharge current will be 0.37 of its maximum value. Anyhow, you will find out that I plot the graph on the negative part. Why? The negative show that the current flow in the opposite directions to that of the current flow during the charging process. Notice that? So this is the direction of current flow through the resistor during the discharging process. It's opposite to the direction of current flow through the resistor during the charging process. If we compare, you see, this is the direction of current during charging process, and this is the direction of current during the discharging process. It's opposite, right? That's why we plot it on the negative part of the graph. Alright, then we find out that the voltage across the capacitor also decreases exponentially with time. When time equal to RC, the voltage is around 0.37 of its maximum or initial value. So we can represent the curve with Q equal to Q0 exponent to the power of negative t over RC. This curve with equation I equal to I0 exponent to the power of negative t over RC, and this curve can be represented by V equal to V naught exponent to the power of negative t over RC. The Q, current, and V is the value of charge, current, and voltage at time t. So class, you'll find that I always label a value of time, RC, on the variation of charge against time, current against time, and voltage against time during the charging and also the discharging process. What actually this value of RC represent? So, the quantity RC that appear in the exponent for all the equations we have in charging and discharging process is what we call time constant, represented by symbol tau. This time constant can be related with the resistance that we connect in the circuit and also the value of the capacitor. So, time constant is a scalar quantity whereby the SI unit is second. It is the measurement of how fast the capacitor able to charge or getting discharged. Okay, so from the relation we find out that our time constant is directly proportional to the value of the resistance and also directly proportional to the value of the capacitance of the capacitors. So it will telling us that the smaller the resistance or the capacitance, the smaller is the time constant and the faster is the charging and the discharging rate of the capacitor and vice versa. So through the time constant we can able to determine whether our capacitor able to charge quickly or it might take a longer time for the charging and discharging process. This is the physical meaning for time constant. During charging process, time constant is defined as the time required for the capacitor to reach 63% of its maximum charge. For example, I represent by this bar. So, fully charged is 100%. So, during time constant, we have already achieved 63% of our maximum charge. So that one we call time constant during charging process. What about discharging process? During discharging process, the time constant is defined as the time required or time taken for the charge on the capacitor to decrease to 37% of its initial or maximum value. It means that initially if my capacitor is fully charged, then the time constant is the time taken for the charge in the capacitor to be reduced until it only left 37%. Okay, so that one is what we call as time constant during the discharging process. So once again, I remind you, time constant is the time taken to reach 63% of fully charged during charging process, or time constant is the time taken for the charge to reduce until 37% during discharging process. Okay, so class, we have come to the end of the videos. So we have discussed all the basic fact or concept about the charging and discharging of capacitors. So you might try to attempt the tutorial 2, question 5, 6, 7, 9 and 10 using the concept you learned through this video about the charging and discharging of capacitors. Thank you for your focus and I shall see you on the next videos. On subtopic 2.3, we have capacitor with dielectric.